Good.
Okay, thank you. So let me start. Can I start now? Okay.
Yes. Yes, please.
Okay. So let me start. I'm Hiroaki Ogata from Japan. Now I'm in Japan, and it's a very pity that I cannot attend the conference in person. But thanks to the organizers' effort, I can give my talk online. Thank you for giving me such an opportunity. Thank you very much. So the title is Model for Higher Order Circular Markov Process, and this is the joint work with Takayuki Shiohama, who will present tomorrow. Okay, so let's move on. The first page. So the target is the circular time series data, okay, especially for multi-order circular Markov process. For such data, we aim to clarify circular autocorrelation, circular version spectral density, and circular version partial autocorrelation. We want to clarify the structure of these three objectives. Okay, so this page is for the brief introduction of the circular statistics, but so far, many presenters talk about the circular statistics, so I don't think we need the basic explanation, introduction of the circular statistics. The circular data is, as you know, the data points, the data represented on the unit circle, and it has periodic properties, so the circular density function small f and the circular distribution capital F becomes like this. Okay, so because of the periodicity. Okay. Then in my talk, we want to consider circular Markov process. Then its construction is based on this Wearley and Johnson's results. Okay, so this is talked in Professor Kato's talk. Today's the first talk of today's talk. So Wearley and Johnson proposed the bivariate circular density by this. Okay, so the circular bivariate density having specified marginal densities F1 and F2. So we can construct the bivariate circular density by this. Here the minus plus, here the sign are both are okay. And this G is any circular density function, arbitrary circular density function. And to unify these two expressions, so we use the notation Q, which takes -1 or 1. So just determine the sign here. So anyway, the joint circular density, and here is its marginals. And this green box part links the joint density and the marginal density. So we can think this part corresponds to the copular density. Okay, so based on this result, we construct the circular Markov process. So we consider circular Markov process theta t. The transition density is constructed as follows. So recall the general form circular bivariate density. So this is nothing but this one. So this is completely same, this one. So now change the arguments here, theta eta to theta t and theta t minus 1. So because we are considering the time series model. So just change the arguments and conditioning on theta t minus 1. So join distribution divided by the marginal of theta t minus 1. So just cancel out here. So we get this one. So this is the transition density function. And finally, we set the marginals as circular uniform distribution. So here becomes 1 over 2 pi, and here is theta t over 2 pi, and here theta t minus 1 over 2 pi. Okay? So here cancel out, and here cancel out, and we get the very simple form. This one, okay? So this is the transition density, and it is called circular. So this is so this function is in today's Professor Kato's talk. We can see we could find this expression. Okay, so this is the anyway. This is the circular Markov process. Transition density of the circular Markov process. Now, we want to extend this Markov process to higher order one, fifth order. So we want to construct the transition density of this order Markov process. And the construction method is very simple, just a mixture of this transition density, like this. So this is our model. So this is called circular mixture transition density model with order P. And here, remind that G is any circular density. Okay. Now, resultant length of Z is denoted by rho Z, and the mean direction of G is denoted by mu Z. Okay. So the more important is this rho Z. Okay. So the mean resultant length of the rho Z controls the dependency strength, the magnitude of the dependency. And the larger rho Z gives the larger dependency strength. Okay? And here mu Z does not affect the dependency strength. So hereafter, the mean direction of Z, mu Z, is set to be 0 for the simplicity. Okay, so here becomes EI0, so becomes 1. Okay. So hereafter, we set mu Z is 0. Okay, then to this model, to this circular mixture transition density model, we want to consider the circular autocorrelation structure, circular spectral density, and circular partial autocorrelation. Okay, first, let us consider the circular autocorrelation. Okay, let's see that be the stationary circular process. And this UT, two-dimensional process, is trigonometric process of theta t, so cosine sine process. And the circular autocorrelation function with log k, denoted by RKC, is defined by this. So more precisely, this one. Okay. And this definition uses the circular correlation coefficient proposed by Fisher and Lee. In fact, the circular correlation is, so far many circular correlation has been proposed, but in this talk we use the Fisher and Lee's circular correlation. to define the circular autocorrelation. Yeah, and this definition is this. Okay, so now we want to clarify the structure of the circular autocorrelation for this MTD model, mixture transition density model. Okay, remind that we set mu z equal to 0, so now z is the transition, the resultant length of z is rho z. Okay. So for this model, for this mixture transition density model, the circular autocorrelation is represented by this. Okay. So this is nothing but this one. This is nothing but this one. So just we just write this part gamma k. So this is nothing but this one. So so what we did is give the recursive expression to calculate this gamma k. Okay. So the gamma k for this model, the gamma k has this recursive structure. So by solving this one, we can get the gamma k. We can get the gamma k. So finally, we get this one, circular autocorrelation function for this model. So looking at this one, looking at this relationship, the structure is very similar to usual ARP model. So this is the autocorrelation function for MTD model. And next, we want to consider the circular spectral density. Okay, recall gamma k is this one. And looking at this equation, so this is the circular autocorrelation function. So the numerator part, it is natural that we regard the numerator part is autocovariance, not autocorrelation, autocovariance function for the circular data. Okay, so determinant of gamma k is naturally, we can regard determinant of gamma k as the circular autocovariance function. And as you know, the spectral density is the Fourier series expansion of the autocovariance function. So the circular spectral density can be defined by the Fourier series expansion of this determinant gamma k. Okay, so like this, we define the circular spectral density. And it is denoted by f theta omega. So for this model, for this circular mixture transition density model, we calculate this circular spectral density like this. This is our second result. So the expression is a little bit complex. So anyway, the circular spectral density for this model is given by this convolution expression. And here, f cosine and f sine is the circular spectral density of cosine and sine process. And here, phi cosine and phi sine is the normal equation of cosine and sine process. The expression is a little bit complex, but it is written by rho z. So rho z is the resultant length of this z, and weight ai, and sine qi here. So anyway, by these components, we can express these objects, and finally, by calculating the convolution of these convolutions, we can get this circular spectral density for this model. So the final expression is convolution, so it is not seen to be explicitly, but this convolution is calculated by the residue theorem, so we can calculate this spectral density. But expression is very complex, so I don't display here. Okay, so this is the circular spectral density, and the final is circular partial autocorrelation function. Okay, again, we consider the cosine sine process ut, and the partial autocorrelation is, roughly speaking, the partial autocorrelation ut and ut minus s is the autocorrelation of ut and ut minus s with deleting the effect of intermediate objects. So autocorrelation with ut and ut minus s, deleting the effect of intermediate variables. So we subtract the effect of intermediate objects like this. Okay? So this epsilon ts minus 1 is ut minus this forward predictor. Using this object, we predict ut, this forward predictor, and subtract this one. Then we get the residuals, forward residuals, epsilon t. And similarly, using the backward predictor, u hat asterisk, and subtract this object, we get the backward residuals. Okay? So looking at this correlation with these two objects, we get the circular partial autocorrelation. So the definition of circular partial autocorrelation is simply the circular correlation of these two objects. So we can define partial autocorrelation like this. Okay. So let's move on to the maximum likelihood estimation of this model. Okay. So again, we consider the MTD model of order P. And here, the parameters to be estimated denoted by eta, which contains the weights, AI, weights, and rho z, so the concentration parameter of the function z, circular density z. So the notation is a little bit confusing, but this rho z cons stands for the concentration parameter of z, and this rho z is the resultant length of the circular density z. So for example, if we set G is rapt Cauchy distribution, this rho z cons and rho z coincides. But if we fit the von Mises, for example, von Mises distribution, the concentration parameter and the resultant length is different. And the P, the model, the order P and the sign Q is not to be considered as a parameter. These two objects is determined by AIC and BIC information criterion, such as AIC and BIC. And the log likelihood function is written by this, and maximizer is the MLE. And target, the true value, classic true value, eta 0 is the maximizer of expectation of this one. So, and we also consider the case that Z is misspecified. Okay, so we can also consider the Z is misspecified case. Then anyway, we can define the maximum likelihood estimator. An assumption for the consistency and asymptotic normality, we assume the several assumptions here. So these are not so strange assumption. This is the usual assumption. So the parameter is convex, compact and interior, and bounded by lower and upper bound and lower bound. The first two derivatives are continuous. Fisher information is non-singular, and the family is identifiable. So these are the common assumptions. And under these assumptions, we get the consistency and asymptotic normality of the maximum likelihood estimator. Okay, then finally we gave a numerical example. So the model is here, and the P is 2, and the weight is 0.3 and 0.7, and this sign we try the all combination of the sign, and G is the Rapt-Kossi distribution. So this is a data generating process. So the remaining time is a few minutes. So this is the circular autocorrelation function. So when Q1, Q2 is 1, 1, it has a positive structure, and minus 1, 1, it has negative, and Q2 is minus 1, then we have the cyclic properties. And this is the circular spectral density. When spectral density in case of Q2 is 1, then Q2 is 1, then we have higher peak like this. And this is a circular partial layer. So it has the similar structure of the AR process. So the circular partial autocorrelation function is cut off. So after the lag 2, right? So this is very interesting results. And simulation results for MLE. So the first is correctly specified case. The data true model is this one, and we estimate the A1 hat, A1 and concentration parameter of G. And as we expected, our MSE decreases as it increases. And when Q2 is 1, strangely, the RMSE is larger than the case of Q2 is minus 1. And this is the misspecified case. The data generating process is this one, the same, and the G is Rapt-Kossi. And fitted model, we misspecified the Z as a von Mises. Sorry, here is von Mises. And von Mises, the concentration parameter is usually denoted by kappa. And now, in the case of von Mises, the resultant length is denoted by this one. So the target is, we estimate this quantity. Okay, so but with misspecified case, we can estimate it properly, and RMC decreases as N increases. So even if the misspecified case, the estimation result is not bad. Okay, so the conclusion. As far as we know, this is the first work to clarify circular autocorrelation, circular spectral density, and circular partial autocorrelation for multi-order circular Markov process. And we give the results of the maximum likelihood estimator, asymptotic property of the maximum likelihood estimator. Okay, now is the time to stop. That's all. Thank you for the listening.
Thank you.